All right, good morning everyone and welcome to my session. My name is Chris and I'm going to speak about the log writer. I just closed the doors. I do not know if more people will come in, but we do not have that much time and I have more material than time. So it's a topic we could speak the entire day, and let's get started with my safe harbor statement as Oracle. I also have a personal one. So everything you're going to see today is undocumented, unfortunately, and everything that I'm going to say relates to Oracle version 1926. The problem with these low-level mechanics is that Oracle doesn't document them and keeps them changing every now and then. So please, if you make different observations from what I have observed, please let me know, because that's always a huge opportunity to learn about new things. With that having said, let's dive into the history of LogWriter. And as you can see based on this chart here, there's quite a lot of innovation in LogWriter, and Oracle does not document them. That is quite sad. And if you look at the history, there have been many enhancements and optimizations. Some of them only applied to Exadata, mostly the newer ones. And there has been a part one the last time. We looked into commit optimizations, and today we're going to look into the other part of LogWriter, which is about writing. And I hear you now, how can it be that writing is so complex? And you will see what Oracle did. It is quite fascinating. So today's part is mainly about this feature here. It goes by the tongue-breaking name Adaptive Scalable LogWriter, and it was introduced back in 12c. There's a new one, and I'm planning to speak about that one the next time in part 3, called Pipelined LogWrite, which is unfortunately only available on Exadata. If you go to the Oracle docs and see what Oracle documented about the LogWriter, it's actually not much. It's just this basic information, something along the lines of there is a log buffer and there is a LogWriter, and that's it. Good thing about that is this is not wrong, but is highly inaccurate, and it leaves out quite a lot of detailed information. So time for us to take a closer look. I don't know, can you hear me like this? Because I find the mic a bit annoying.
For the recording, maybe the mic.
Uh-huh.
It is for the recording. We can't hear you in the back, really.
Yeah, let's try that. I can move around better. All right, let's get started with some LogWriter fundamentals. So transactional performance in Oracle is mainly about two parts. First, the speed of writing redo records down from the log buffer to the disk. And second, we have to inform and notify all the sessions waiting for a commit that their commit is complete. These are the two fundamental parts. And just to quickly get us all aligned what that looks like in more detail, maybe also for those who have missed the first part, let's assume we have a foreground process and the LogWriter process. And historically, this is what happened in Oracle. So we have a session doing work, attempting to commit. It goes and posts LogWriter. LogWriter starts the writing, emits a log file parallel write wait event, and when done, posts back to the committing session that the wait is now complete and that the transaction has been persisted to disk. And during that time, the foreground and the session, it waits on a log file sync wait event. This is the historical model that has been the case through versions, I think 10 or so. And then in 11, Oracle started adding optimizations. And the main optimization was the one we looked into. It's called Adaptive Log File Sync. And what Oracle did is they made the commit, or they turned the commit notification upside down. So we no longer have LogWriter informing sessions that a commit is complete, but rather we have the sessions going there actively polling the status and the write progress of LogWriter. And with that, we can save, in some situations, some time, because LogWriter can run into delays when it gets scheduled on the operating system, especially under high load. So this makes the commits faster from this perspective of a foreground process. And there are various enhancements and optimizations that have been added over the years. Just quickly summarize them here, but I'm not going to comment too much about them. The most recent one on Exadata added a spin component, so rather than sleeping, these sessions can actively spin and probe on CPU while checking the progress of LogWriter. The feature goes by the name Adaptive Log File Sync, and the main idea behind it is that Oracle can dynamically switch between these two modes, meaning it under light load, moderate load, it uses a post-wait scheme, and under higher load, it starts using the polling. And if you draw that on a line, it looks like that. Depending on load, there is a break-even point along these lines when Oracle decides to switch. And the last time we looked into the mechanics and all the formulas and heuristics that decide about the switching. And the cool thing about that is Oracle gives you the best of both worlds. So if load is light, there's an optimization for light load, and if load starts increasing, there's an optimization for high load, and Oracle switches back and forth as system load changes. That is the first part of log writer and commit performance, and now we're going to cover the writing part, and it has also the name adaptive in it. And that also means there is a dynamic component at play in the background on all your systems. And unfortunately, that dynamic is not exposed that much. So if you don't go and actively look for it, you will not see it. But what's the idea? There is a log writer process. There has always been a log writer process as far as I can think back. And the log writer process writes to the redo log. It's a single process. And that means, yeah, it is limited in terms of what it can achieve throughput-wise. So a single process cannot dump down gigabytes of data per second. For that, we need to parallelize. But parallelization has the disadvantage that it implies coordination. And coordination in computing terms is always expensive because you have log writer, and log writer needs to coordinate writes between multiple worker processes. And now what Oracle did is similar to the adaptive log file sync mechanism. It added a dynamic. And the way, high-level summary, the way it goes is at runtime, Oracle starts in single mode with a single log writer. It keeps on measuring the write throughput. And if the write throughput reaches a certain threshold, it switches to scalable mode. And then in scalable mode, log writer becomes just the coordinator and just assigns write and write work to multiple worker processes, which then write into the redo log. And while in scalable mode, Oracle keeps on measuring system performance. And what it does is it no longer measures the throughput, it measures the write time. And if the write time drops below a certain threshold, it switches back to single mode. That's the main idea. And we're now going to dive into all these details, what that means in the background. But first, some concepts. So, as mentioned, log writer in scalable mode becomes a coordinator, and it coordinates writes across multiple workers, and the workers are grouped in what is called a group. And displayed here we have 4 groups, and the number of groups is defined by this underscore parameter. That is limited to an absolute maximum of 16. So on larger systems, it cannot exceed the number of 16. And if we zoom into that, if we zoom into a group, the way it conceptually works is every group has something called a head worker, and the head worker is responsible for doing serial operations. So even if there is a parallel write, we're going to look into that, there are some portions of a write that cannot run in parallel. Things like updating the progress status of the write in the SGA is a serial operation, and serial operations like that are always carried out by the head worker. And that means there's quite some intricacies and complexities involved when it comes to coordinating the writes across the groups and within the group. Similar to the previous parameter, there is also a maximum how many workers we can get assigned to a group, and that is defined by max log write parallelism. Interestingly, the number of workers per group is computed at runtime. For every single log writer goes there and decides how many of these workers to assign to a group and how many of the writes to assign to multiple workers. But we'll come to that in more detail. So that also means the total number of workers per instance is just the multiplication of the number of groups we have multiplied by the number of, or the degree of the parallelism per group. And the defaults for these parameters, the first one, outstanding log writes, it's hard-coded in the binary. I do not know why, but it's always set to 2, at least based on what I have seen. And the second one, the max log write parallelism, is derived from the number of public redo strands in the log buffer. It's just the number of public redo strands divided by 4. And the number of redo strands is derived from the number of CPU, from the CPU count that is set on your system. So let's assume for just a moment we were an Oracle kernel developer and we were tasked to implement the scalable log writer and to add parallelism to redo writing. There are a few patterns or a few options how we could go and implement that. The most straightforward one, very simple. We have a log buffer. We just go there, we grab the entire log buffer, the entire chunk of redo data, and we just write it down to disk in a single write. That gives us a large write, and large writes are not that nice because they take a lot of time and they are susceptible to outlier response time. So the larger the write, the higher the risk that the write gets delayed, unfortunately. So what we can do is we can divide the log buffer into chunks, and then we can just work on these chunks in serial, one by one, shown here on the screen. And also let's assume this takes roughly the same time as this one. So in generic terms, let's assume this takes 5 time units, and this one takes 5 time units as well. And if we want to optimize that, what we can do is we can do pipelined writes. And pipeline means overlapped. So log writer can go there, grab a chunk in memory, assign it to a worker, and then immediately after, while the first worker is in progress, assign another chunk to the second one, the third one, fourth one, etc. And this is what we mean by pipelined or overlapped writes. And log writer, this is by the way the default mode. When log writer switches from single to scalable mode, log writer then uses pipelined or overlapped writes. There is some overhead attached to this because we need coordination. This is shown in the red boxes there in the upper and lower part of the slide. But when we compare that, we have 5 time units, and here, let's assume we have 3 time units. So we can save some time in writing. There's another option, and that shows the difference between concurrency and parallelism. We can also assign multiple workers to work on a write or to cooperate on a write together. And in this case, let's assume we have 5 workers working on a large write in parallel. And because everything completes together, we can even save more time. And in this case, let's assume it just takes 2 time units. What is interesting is that log writer starts in pipeline mode and in certain situations switches to parallel mode, and that decision is taken at runtime. We'll cover that a bit later. And what log writer also does, and that is quite interesting, it combines these two approaches. So it can issue overlapped and pipelined writes and parallelize individual pipelined writes, and that looks like that. It's like a combination of the two methods. So this is an attempt to classify the write modes. On the left-hand side, single mode, and then we have scalable mode with parallel writes and concurrent writes. And there is a new thing on Exadata only. It's called pipelined writes. It's a marketing name, but it's very misleading because pipelined writes have been in log writer ever since. So I do not know why Oracle calls them pipelined writes, because more strictly speaking, they should be called pipelined writes with size regulation, because on Exadata, log writer actively measures the write size so that it always finds the most ideal write size at runtime for a certain workload. But that is something to be covered the next time. So this is again showing the write mechanics, but this time including the redo log buffer and the public redo strands, because they play a central role in how log writer works. When log writer does a write, it has before the write the phase called the gathering, and gathering is basically just collecting. So it goes to the redo log buffer, checks how much data is in every strand, packs that into one kind of logical unit, which is called the LWN. And it's not officially documented what it means, but I think it is a log write number or something like a logical write number. And I prefer the term logical write number because if the IO is then assigned to multiple workers, the workers get a chunk of that logical write assigned, and on the operating system level at the syscall interface, these chunks can get further split into smaller physical IO requests. And this here is showing a parallel write. So if we have a parallel write, it means we have multiple workers on the same LWN logical unit at the same time. Whereas here on the next slide, we can see a pipelined write And that essentially just means we have two different groups working on two different LWN units concurrently. And here, for the sake of completeness, the combination of pipelined and parallel writes at the same time. So key message here, log writer internally operates in LWNs, so logical writes. And these writes then get assigned and further broken down into physical I/O requests. Now the interesting questions, when you look at that, and this has been bothering me for quite some time, and there was no documentation, so I started investigating. Questions like, when do we switch from single to scalable, back from scalable to single mode, and what if we have too many log writer mode switches, and when does log writer issue pipelined write, and when does it issue parallelized write? So the first one, when do we switch from single to scalable mode? This is the decision-making criteria. It is, in simple terms, when the redo rate is higher than the switch threshold multiplied by 2. And now, I see you asking, okay, what is the redo rate? What is the switch threshold? We'll get to that. The redo rate is basically just the volume of redo that gets generated within a time. So in this case, it is the redo size statistic that you can look up in VDollar/systat, and it's the CKPT, the checkpoint process, which measures that every 3 seconds, and then it computes an average. That is the redo rate, and it's compared to the switch rate. And the switch rate is nothing but the redo rate at the previous point in time when we switched back from scalable to single mode. So it's a historical value of the redo rate. That is also, by the way, we'll come to that, a drawback of that model, because it's based on a past situation which may no longer reflect reality. But for the moment, just keep that in mind. When the redo rate exceeds the switch threshold by a factor of 2, log writer switches from single to scalable mode. Interestingly, the redo rate is not a normal average, it's a moving average, and it's based on this formula here. Oracle just takes the difference between current value, previous value 3 seconds ago, and then computes a deviation and the delta with the redo rate, and then it multiplies this by a factor of 2 over 129. And you'll see that in many places in log writer internals that Oracle is using this kind of formula. And what that basically does is it smooths out short-term fluctuations, and on every update, we increase or decrease the average by something like 1.55%. Because we do not want to overreact to short-term load fluctuations on the system. When you do this kind of low-level investigation, you find interesting things that make you scratch your head or that make you even despair. I started out on an Exadata X8M, and what I found that wherever a PMEM log is used, the switch threshold changes. And on Exadata X8M and X9M with a PMEM log activated, the switch threshold is multiplied by a factor of 4 for whatever reason. It's just hard-coded in the Oracle binary and you cannot change it. You just need to be aware of that. So you may observe different log writer behavior across different platforms for multiple reasons. Here again, everything in a single slide with some more details. This multiplier that I showed, 2 for non-Exadata and 4 for Exadata with PMEM log, is actually driven by this underscore parameter, which defaults to a value of 200, meaning 200%. So if you change that, of course, you change all the log writer mechanics and computations. The switching is not really that prominently exposed. There is a log writer trace file, and you can go and look into that. And if you do that, you can see information like the following here. And I just provided a short example. Based on what we know now, we can interpret these figures, and we know we need to compare the redo rate against the switch rate. And if they are, or if the redo rate exceeds the switch rate by a factor of 2 or 4 respectively, then log writer will perform a switch. And I wish this kind of information were more publicly documented than it is. When does log writer switch back? Summary, when the write time in single mode is faster than the write time in scalable mode. And behind this simple comparison here is quite a lot of complexity. It's not as simple as the switch from single to scalable mode. And I try to summarize it like here. There is again a complexity involved. It depends on the setting of that max log parallelism. If it is set to 1, which is a special case that also only applies to Exadata X8M and X9M because of the PMEM log, then Oracle uses the read-to-write average, whereas if log parallelism is higher than 1, it uses the effectively measured read-to-write time when a write is performed. So again, log writer switches back when the single write time is faster than the write time in scalable mode. And single write time is measured like this. Oracle basically just takes the time for a single write either based on average or on effective time, and then multiplies it by the number of concurrent writes that you can have on a system. And this is a model. This may not necessarily reflect reality. It's really just a heuristic. Here is a low-level trace of what happens when you do an instance startup, just to illustrate the point. Oracle on startup uses a certain default for the log parallelism, in my case 4, and then it calls a function to check what storage is allocated on the system and on Exadata. If it detects it's an X8M or an X9M, it just overrides that default and sets it to a fixed value of 1. And this then messes up all the computations. That makes life quite difficult. But again, it only occurs on PMEM-based systems, and they are quite dated as of today, and they will disappear because Intel is no longer producing the PMEM. The read-to-write time is also, or the average read-to-write time, similar to what we observed, is also a moving average, and they again use that multiplier of 2 over 129 to smoothen out short-term fluctuations. And secondly, what you could also see on the previous slide, when that special case kicks in, the worker delay is also factored into the equation. And the worker delay is basically just that section of time here when log writer assigns a write to a worker and then posts the worker to start working. And if there's a time difference, that worker delay statistic is getting incremented. So it's also factored into the calculation. And again, it's also a moving average based on the formula that we just looked at. And as mentioned, that is visible in quite a few places. And it's also CKPT who does that computation. So checkpoint process, not only checkpoints, it is also used for calculating various system statistics at runtime. And here's how it goes, what Oracle does. I'll give you a short version. You can study and look up the formula at home. So the scalable model, it just assumes how much time do we need if there were only a single log writer. Then it calculates how much time do we need for overlapped writes, and then it kind of interpolates the two. And in short, what it does, it just subtracts the time of overlapped writes from the single writes, and out comes a number, and that number is called scalable. And we can also see that in these log writer traces, and can fill in the values for all these formulas and interpret. And if we did the math correctly, we will see in this case we have a time of 1,722 for a single write in single mode, and 3,247 for writes in scalable mode. And if I recall correctly, these times are measured in microseconds. And in this case here, because the single time is less than the scalable time, log writer decides to switch back from scalable to single mode. I haven't mentioned that, but it's important because the switch threshold that we looked at a few minutes ago, it's not a static value. Oracle keeps on changing and updating it over time. To be precise, it keeps on aging it, and that means the value decreases over time to make a switch more likely. And I do not know exactly the reason why that is, but I could imagine situations when the redo volume is very high and that switch threshold is set to quite a high value. This may prevent situations, or this may prevent LogWriter from switching the mode. So I guess that's the reason why they keep on decreasing that value over time. And the way they decrease it is by 0.01% on every time when they perform an evaluation if a switch should occur or not. And the evaluations are also protected by guardrails, so we do not want to have LogWriter keep on flipping back and forth between single and scalable mode. And the guardrails are based on sampling. There's a time guardrail, a count guardrail, and an arbiter. And what that means is the sampling time is defined in seconds, so there must at least pass 3 seconds between a mode switch, and there must at least be more than 128 redo writes, and there is an arbiter counter which defaults to 3, and a mode switch only occurs if all these conditions are fulfilled. So more than 3 seconds, more than 128 redo writes, and arbiter counted down from 3 to 0. That means, roughly speaking, a mode switch can only occur every 9 seconds at maximum, not more. Now to the question, when does LogWriter do a concurrent write, a pipelined write, and when does it do a parallel write? That is also something not in the docs, and the factors are listed here. So we need at least 1 megabyte of redo to be written. If we have less than 1 megabyte of redo in the redo strands in memory, LogWriter will never parallelize a write. It'll only issue pipelined writes in scalable mode. And interestingly, the second factor that caught me by surprise, we must have more than one public redo strand in use. And the public redo strands, they only get activated when there is contention on the redo allocation latches. By default, if there's just a single process filling redo into the redo log buffer, writes will very likely not get parallelized. And the last factor is, of course, the max log write parallelism is kind of implied. If we have a parallelism of 1, we effectively switch off parallelism, and so writes do not get parallelized. This is the formulas that is used. I have a better example here on this slide. What Oracle does is it checks how many public redo strands do we have, how many of these strands are active, and then it calculates an average of strands per worker. It checks at runtime next what is the highest active strand that we have, and then it just kind of divides these values. And in this example here, with 8 strands, 4 of them active, we get a parallelism of 2. I kind of brute force this into a heat map with an example of 16 strands. And you can look up, based on your number of public redo strands that you have and your log write parallelism, how many workers Oracle may assign to a parallel write, provided that there is at least 1 megabyte of redo in the log buffer and more than 1 strand is active. There are a bunch of systat counters in VDOR systat that show you what LogWriter is doing behind the scenes, but they are, again, not that well documented, so I just added them here. I'm not going to read through them now to save some time, but it's basically just the number of writes and how much time do we spend in that worker delay, etc. How much time is left? 10 minutes. I mentioned it, there is coordination involved and synchronization. We have coordination between multiple groups and we have coordination within a group. I tried to provide an example here for a parallel write. It's quite complex and we don't have that much time left. So I'll try to give you the short version. What this is showing here is a parallel write. So we have LogWriter assigning a redo write to 2 workers. And these 2 workers start working on that write together. But then one worker runs into a delay, this guy here. And when this guy runs into a delay, the first one cannot proceed, it needs to wait. And that waiting is coordinated via semaphores. So it starts a wait, and only when this second write here completes and sends a post to the first one, can the first one complete and signal back to log writer process 1 that it's now done, and it also needs to post log writer so that log writer is aware that it can send new work to other workers. And you can see based on, that's a simple example, there can be way more complex example, and that coordination is expensive. And there is quite some overhead involved. And every time we have these coordination points and signaling back and forth between processes, it could be that we run into a delay because the operating system doesn't schedule us in time. So this is the reason why this is mainly a throughput-oriented feature and not a latency-oriented feature. So what are the drawbacks? First one is it's based on heuristics. We looked briefly into the formulas, and there are some assumptions behind these formulas. And unfortunately, it doesn't mean that these assumptions are always true. So it could be that what Oracle assumes in terms of how many writes are pipelined, how much time we can save by doing pipelined writes, is not reflecting reality. And it doesn't adapt to system load changes within a reasonable time. So actually it's quite slow to adapt to changing conditions. And I think that is the reason why Oracle added a new feature and enhancement for Exadata systems, to make the system more responsive to changes in workload conditions. And second drawback, what can happen is, especially with large writes, depicted here, let's assume a situation we have multiple chunks of redo to be written from the log buffer down to disk. Log writer assigns these chunks in pipelined fashion to multiple workers. And let's assume log writer 00 starts working on a large portion. Let's say it works on 1 megabyte. And then immediately after, the other writes that are assigned to the other workers, they are rather small. What happens in this situation is that the large write is very likely to take much more time than the shorter writes. And when this situation kicks in, the pipeline stalls. You can think of all these writes going through a pipeline, and if not every worker can actively work on a write at the same time, the pipeline comes to a halt, and we have these stalls. It's depicted here by these dotted lines. So we have many workers assigned. We need to coordinate between the workers, but we cannot achieve the maximum possible throughput because we have these stalls. No, nothing. So the question was if there are any statistics showing if there's stalls in the pipeline. No. And actually I was thinking of trying to measure that with BPF, but I haven't had time to look into that yet.
Would it help you if there were?
Potentially. I mean, yes, every instrumentation is useful, so if you can add it, please add it. Of course. And importantly, the larger the writes and the higher the number of large writes, the more susceptible you are to I/O response time outliers, making this kind of situation more likely. And what I also need to add, the heuristic doesn't check the write size. So when log writer assigns a parallel write, it just takes the largest possible chunks and blindly assigns it to a worker, and it doesn't go and check, would it maybe make sense to split that large request into multiple smaller ones? That's what happens with the Exadata optimization, which measures the write size and recomputes it dynamically at runtime. But with this model, adaptive scalable log writer, it just blindly assigns the work to the writers, and very likely we often end up in a situation like that, and the pipeline stalls, reducing and restricting the possible write throughput. Yeah, I keep on referring to this Exadata feature, and just maybe a short preview on how it works at the high level. On Exadata pipeline log writes, they only issue a write immediately if there is no active write in progress. And there are two thresholds, a write size threshold and a timeout threshold. And what the write threshold does is it is recomputed at runtime based on various statistics. Oracle computes what is the ideal write size for the given workload right now, and only if that write size is reached it issues an IO. And while waiting for the right size to be accumulated in the log buffer, it waits until a timeout is exceeded in order not to penalize the committing sessions too much. And while LogWriter is writing, that is quite interesting, it doesn't go to sleep because sleeping implies we have to wake up. Wake up implies scheduling delays and makes things slower. So LogWriter actively spins on CPU. And there's a new wait event introduced for this kind of wait scenario. But I'm planning to cover that the next time. So if we dive into this feature, there's always the questions, how does it interact with other ones? And this one is documented. Adaptive Scalable LogWriter is not compatible with DataGuard in sync transport mode. So if you go from, let's say, max performance to max availability mode, Oracle will switch off the multiple LogWriter feature. So LogWriter will, by default, then become a single process. And what happens in the background is there's a flag in the SGA, and whenever a write is submitted, Oracle checks if that flag is set, and if it is set, it never switches a mode from single to scalable. And all these metrics, they are centrally managed in the SGA. If you take an SGA dump, you can find them in the raw memory structure. It's called KCRF slave info, and on the right-hand side, the functions and the details, how these values are managed. Why is that important? Because we can attach to any Oracle process and we can fiddle with these values. So just to prove the point that what I'm telling you today is kind of true and not something I invented, trying to do a demo here. Hope it'll work. So here we have the LogWriter trace file on the right-hand side, and I'm now attaching with that LogWriter control script to any Oracle process, the one here with this PID. I just need any process so that I can modify values in the SGA, attach to it, and have a bunch of GDB commands. This one just shows what LogWriter is doing, retrieving the values from the SGA. We can see here, okay, it's running in serial mode is heuristic, etc. And the fast sync is enabled. That's the Exadata commit optimization from part 1. And there's another command that I added. It's called enable LG workers. And in this case, it says, okay, I cannot do that because fast sync is enabled. We need to switch it off first. And what it does is it just goes there and modifies a value in the SGA. And if we check again, we can see fast sync is now disabled. And with fast sync disabled, we should now be able to enable the workers. And here's the entry in the LogWriter trace file that these workers have indeed been enabled. And what that script does is it just goes there and uses the formula I showed you and modifies the values in such a way that next time LogWriter submits something to write, everything is rigged in such a way that a mode switch is triggered. Yeah, and with that, I think time is up. If any questions, please ask or catch me later outside over a coffee or a drink. Thank you very much for attending.